Is a measure of how hot or how cold something is, and we had looked at a couple different or three different temperature scales that we talked about back in chapter 1 or chapter 2, the Celsius, the Fahrenheit, and the Kelvin scale. And then we ended up looking at how we can convert between the Fahrenheit and Celsius, or between Celsius and Fahrenheit, right? So we looked at a couple of these equations down here. It's important when you're using these equations that you do the operations in the correct order. All right, so let's take a look at an example just to get us back up to speed. So it says the typical temperature in a room like this one is about 21 degrees Celsius. What is that temperature in degrees Fahrenheit? So here we want to go from degrees Celsius to degrees Fahrenheit. So we're going to use the relevant relationship, which is this equation down here, and all we need to do is, if we're provided with a degree Celsius, is go ahead and stick it into our equation. So when you use this equation, you want to make sure that you, like I said, do the operation in the correct order, right? So our Fahrenheit temperature, and that's how we can abbreviate Fahrenheit. T for temperature, subscript F means it's in degrees Fahrenheit, is 1.8 times whatever the Celsius temperature is, which in this case is 21. And then we're going to add 32 to it, right? So you want to multiply the Celsius temperature by 1.8 first, and then we're going to add 32 to it. All right, and what do we get for a Fahrenheit temperature? You might have to use your calculator, right? Most likely. 60? 69.8? Does that temperature make sense in terms of what you know about Fahrenheit temperature and what you're experiencing right now, right? So, on a typical day like today outside, it's maybe about 40-45 degrees Fahrenheit, which is kind of chilly. So it makes sense that in here it's close to 70, which is maybe not the most comfortable temperature, but it is bearable, right? So the answer here makes sense, and you always want to double check that it does make sense in any calculation that you do, whether it's Fahrenheit or temperature, or whether it is any other operation that you're doing. So that's how we go from Celsius to Fahrenheit. We also saw another equation that we can use to go from Fahrenheit back to Celsius. The third temperature scale is the Kelvin temperature scale, and we saw the relationship between that and the other two when we compared them on Monday. When we go between the Kelvin temperature scale and the other scale, specifically the Celsius temperature scale, the conversion here is actually a lot simpler. Right, so we're just going to add 273 to whatever that Celsius temperature is. And why do we add 273? Well, that 273 comes from over here, right? So 273 on the Kelvin scale actually corresponds to 0 on the Celsius scale. So the numbers that you see in those conversions are not just numbers that we pull out of thin air. They actually come from the comparison of the scales themselves, right? So we're going to add 273 to whatever the Celsius temperature is to convert it to the Kelvin temperature. And remember, when we deal with the Kelvin scale, it's not degree Kelvin, it is just Kelvin. So body temperature oscillates, right? It's not constant. It goes up, it goes down a little bit. But typically, on average, we can say it's 37 degrees Celsius. And what is that in Kelvin? Well, we're going to take the degrees Celsius and we're going to add 273. All right, so 37 plus 273. Right? Maybe you can do that in your head. If not, use your calculator. And that'll give us 310 as the Kelvin temperature, right? So compared to the Celsius, the Fahrenheit, a little bit simpler, but it still involves a little bit of math. right? And math is something you cannot run away from in chemistry, okay? It's going to follow you like a tail, always. Okay, and then as you probably know, just to sort of give you a perspective on the temperature and temperature scales, we just said, typical body temperature is around 37 degrees Celsius, but it actually falls within a range, right? So nobody's body temperature is going to be exactly at 37 degrees throughout the entire day. It goes up a little bit, it goes down a little bit, depending on whether you're moving around, whether you're sleeping, whether you're outside, whether you're inside. But it normally hovers in a sort of a 2 degrees Celsius range, which corresponds to this range here in the Fahrenheit temperature scale. If the temperature starts to drop below that, right, then you suffer from a condition known as hypothermia, right? So hypo here means lower than what it should be, right? So you get cold, in other words, you start to shiver, and your body kicks into its response to being cold to generate more heat. Alternatively, if your temperature ends up being higher than what the normal range is, you end up suffering from a condition known as, well, fever, first of all. If it gets high enough, you suffer from hyperthermia. Okay, so I'm stressing these terms here a little bit because we're actually going to see these down the road. So hypo, like low, and then hyper, like hyperactive, overly active, right? Hyperthermia, overly hot, or overly therm, and thermic would mean hot, right? So there are little clues you can use in the name for things to actually figure out what they actually mean. You probably, if you're in your anatomy classes, you probably know some of those little tricks you can use. All right, so that's our quick discussion of temperature. The next thing, the last three sections here that we're going to take a look at in chapter 3 deal with energy. All right, and we're going to focus in on just a general introduction to energy, and then we're going to see how it plays a role in changes to a substance, whether it's physical changes specifically here, and then we'll see down the road in subsequent chapters chemical changes as well. All right, so when we had defined chemistry, we said chemistry was the study of matter, the changes that matter undergoes, as well as the energy associated with those changes. Right? So we talked in a little bit of detail about matter in general. We were able to classify it, pure substance versus mixture, and then we saw some subcategories. We also talked about the changes that matter can undergo, chemical changes versus physical changes. Now we're going to take a look at the energy aspect of that definition. So let's first of all define what energy is. So we can say that energy is equal to the ability or capacity to do work, right? So that's a very simple idea, very simple definition, but it gets to the point. You have a lot of energy, you can do a bunch of stuff. You don't have a lot of energy, you can't do a lot of stuff. You can't do a lot of work. Right? So it's not overly technical, but it still addresses what energy is. Now, when we start looking at the different types of energy, there are several ways by which we can classify energy. One of the more common ways that we can distinguish different types of energy from each other is whether it is considered kinetic energy or whether we're looking at potential energy. So how are they defined, and what are some examples of each of these? Well, kinetic energy can be defined as the energy of motion. Right? So anything that is moving is going to possess kinetic energy. That's what the term kinetic actually means. movement. So anything moving has KE, and KE is but it is the abbreviation for kinetic energy. What's an example of kinetic energy? Running. Right? Your arms are moving, your legs are moving. Another example.
Your car rolling down the road.
Your car rolling down the road, or even going up a hill, right? As long as it's moving. So let's just say a moving car. Or a spinning fan blade. Okay? Anything that is moving is going to have kinetic energy associated with it. Me waving my arm like this, that's kinetic energy. And that's different than potential energy. And what potential energy can be defined as is the energy due to a substance's position, in other words, where it is, or composition. Where is it, or what is it made up of? So what would be an example of potential energy? Something has the potential to generate energy, in other words. Sorry? A sitting car? So what about the car specifically has potential energy associated with it? Where is it sitting? Top of a hill, bottom of a hill, middle of a hill? Flat surface? On top of the hill? Okay, so there's this pen, right, and I'm holding it, and it's not moving. What type of energy will it possess? Kinetic or potential? Potential, right, just based on where it happens to be. And if I let it go, right, then it starts to move, and then that energy, due to its position, the fact that it's high up in the air, means that it has the potential to generate energy, and that energy gets converted to kinetic energy, the energy of motion. So there's an inter-conversion of those two types of energy, right? So I have to expend energy to actually lift the pen back up in the air to give it some potential energy, and then I release it, it turns into kinetic energy, the energy of motion. Well, it hits the table. Where does the energy go? Does the energy just disappear, do you think? Do you think energy can be destroyed? What's happening to the energy? So potential energy due to the position, kinetic energy, as it moves, then it hits the table. So you hear something, right? That noise, that's a form of energy, actually, sound energy. So the potential energy gets converted to kinetic energy, the energy of motion. And when it hits the table, the energy of motion gets converted to sound energy. And then also what you can't see, what's happening on a microscopic level, is the particles here in the table actually start to vibrate a little bit more. So it gets converted to even more kinetic energy within the particles of the solid. And there's also a little bit of heat energy that gets created as well. Right? So all those different forms of energy that are created, or not created, but transformed, are not as useful as other types of energy. Right? So the energy gets dissipated into less useful forms, but there still is the conversion of energy. And the main one here we're looking at is potential to kinetic energy. All right, so potential energy here would be, an example of that would be, if I hold a pen up in the air, or if you go back to our little diagram here, or picture, water that's held behind a dam. So based on where the water is, it has the potential to generate energy. And if we allow that water to move now, for instance, through the dam, and we funnel it through turbines, for instance, we can use the kinetic energy of water as it gets converted from potential to kinetic energy. We can use that to generate electrical energy that allows us the lights to light up, light energy. Right, so there's a whole interconversion of all different types of energy. Another example of potential energy that we may not think about is the potential energy due to something's composition. What is it made up of? And good examples of this would be things like fuels. Right, just based on their composition. So the forces that hold the compounds together, when we break those forces of attraction, that actually releases a bunch of energy, right? And fuels are really good examples of that. So for instance, things like gasoline would be an example of something that has potential energy, right? Gasoline is the fuel for your car. What's the fuel for you? Food. Right, so whatever, sugars, carbohydrates, proteins, right? Based on what those things are composed of, they have the potential to generate energy when your body starts to break it down, right? And that's sort of important, right? That allows you to do what you're able to do on a regular basis. All right, let's take a look. Potential or kinetic for these options. Rollerblading. This would be kinetic energy, right? You're moving around on rollerblades. Peanut butter and jelly sandwich. Potential, right? That's food. Mowing the lawn. Kinetic energy. And then gasoline would be the food for your car, right? So that has the potential to generate energy based on its composition. So those are the two main types of energy that we can distinguish. When we get further down into the course, we're going to see other types of energy as well. All right, so when we start looking at energy, just like with all the other things that we can measure, there are units that we're going to see that we associate with energy, and specifically in chemistry, we're going to be looking at energy changes due to heat changes, right? So heat is also known as thermal energy, and this is most commonly, or the most common form of energy seen in chemistry. We can measure thermal energy and heat changes. And this is associated with the particles of a sample and how fast they're moving around. Right? So the more motion, the faster the particles move, the greater that thermal energy or the heat energy is going to be. The unit of energy that we use in the SI system, not just for energy but also for work, is called the joule. All right, and joule has the abbreviation big J. Uppercase J is joule. Has anybody heard about the joule before? Okay, the joule itself is kind of a small unit of energy, so we actually use the kilojoule as a more appropriate or more applicable unit of energy. Right, so remember that K there means kilo, so this stands for kilojoule. And a kilo of anything, according to your metric relationship, always means 1,000 of that thing, right? So a kilojoule would be 1,000 joules. And that is an equality. If you wanted to, you can use it as a conversion factor. Or you can flip it to get the other conversion factor. Right, so this relationship here, kilo to the base unit, this is nothing new. The only thing now is we're sticking kilo in front of a base unit to give us that bigger unit of measurement. All right, so joule, the SI unit of energy, is what we typically see. Kilojoule is maybe a little bit more reasonable in terms of the amounts that we're going to encounter. Well, how much energy is actually expended or used to do normal everyday things? So if you look down here on the bottom, right, when you're sleeping, right, you use for about 1 hour about 10 to the 5 or about 100,000 joules. Now this is assuming that you're sleeping and you're not sleepwalking or sleep running or sleep jumping, right? You're just laying there doing not a whole lot of nothing. So not a whole lot of energy that's used. The energy that you get from one serving of pasta or from a donut, a regular sized donut, or what you need to bite for an hour or so, is 10 to the 6 or about a million joules. Energy from 1 gallon of gasoline, right? 10 to the 8 or 100 million joules. And then as we keep going up and up and up, you'll see that the amounts of energy actually increase tremendously. So I want to draw your attention up here. So the world reserves of fossil fuel, based on what we know right now, is about 10 to the 23 joules, right? So 1 and 23 zeros. That's a huge number, a huge amount of energy that we can tap into. But look at the thing right above it. So it says the energy radiated by the sun in 1 second is 10 to the 26. So the sun puts out in 1 second 1,000 more times energy than all the fossil fuel on our planet in 1 second. How long has the sun been around? Longer than you have been here. Right? Longer than your parents have been around, longer than your grandparents, longer than your great. So the sun has been around for a long time, and it's going to be around for a much longer time afterwards. And every single second, it's giving off a whole bunch of energy. That's kind of like free energy, right? You don't have to pay for it. And guess what? There are certain things on this planet that can take that energy and use it. What are those things? Those are your plants. Not your plants, but plants in general, right? They take the sun's energy and they convert it to other types of energy, like food or sugars that we can then eat and get energy from it, right? We're not fortunate enough. We don't have the tools in our skin or in our bodies to take solar energy from the sun and convert it into useful forms. We have to depend on other things, right? So when you hear about, the development of things like solar cells and solar panels that take that sun's energy, right? That's why there's a lot of research and interest in that, because the sun's going to be there for a long time, and if you can harness that energy, you can get a ton, not a literal ton, but you can get a lot of energy from it. All right, so joules is the SI unit of energy. A more common unit of energy that you're going to see is the calorie, right? And you're going to see the calorie more so when it comes to nutrition. The calorie is related to the joules according to this relationship. So 1 calorie is just over 4 joules. That's an exact relationship. You do not need to memorize this. Okay, if you need it, you're going to be provided with it. That's an equality. We can use it to come up with our 2 conversion factors, right? Just like we would with any equality. Similarly, the calorie itself, 1 calorie is kind of a small unit. So we actually use kilocal as a more appropriate unit of energy, especially when it comes to nutrition and the energy content of foods. And a kilocal here would be 1,000 regular calories. Right, so everything that you eat or drink that comes in a package is going to have a label on it that tells you what is in it, but it also gives you the energy content of that thing, usually per serving or per packet of that, whatever that happens to be. Right, and then the next section here we're going to take a look at is going to focus on where we see where we're going to use some of that energy in the food stuff that we eat or drink. All right, questions so far on our brief intro into the world of energy. So we've talked about what energy is, the different types, the two general types of energy, kinetic versus potential, and then we've looked at some of the units that we are going to encounter when we deal with energy. So I mentioned before, we have energy associated, potential energy associated with all the stuff that we eat or drink. What does your body prefer to use for energy? What type of food stuff? Sugars? Sugars are your body's preferred energy source, right? So if it has a choice, right, it's going to use carbohydrates or sugars. And that's because your body has evolved really efficient mechanisms for breaking down sugars to give you a bunch of energy. Right? There are many, many, many types of sugars around. Carbohydrates, by the way, is just a fancy word for sugars, or a complicated word for a simple thing, like I mentioned on Monday. When your body has exhausted your supply of carbs or sugars, then it is going to tap into your fat reserves, right? And your fats are things like, you may hear the term lipids. So it uses the sugars first. We use all of those and we get to the fats, and then if we exhaust our fat supplies, then we tap into our proteins, right? And if you're getting to that point, that means your diet is not a good one, right? If you have to start breaking down your proteins to get energy, that means you're in a dire situation, right? Because proteins are extremely important. They help. They're in your muscles. They're in your hair. They're in your skin and your nails. They're all over the place. So you really don't want to get to that point. But if it needs to, the body can start using proteins for energy as well. So this is the general hierarchy in terms of what it will prefer to use to generate energy to allow you to function effectively. All right, so I mentioned that in nutrition we're going to use the calorie. We're going to see the calorie as the most common unit of energy. And actually, if you look, I'm not sure if anybody has any sort of packaged food with them right now, you can take a quick look at it. On the back of it, it'll actually tell you what the energy content of that thing is, right? So here we have, this is a label, nutrition label from a snack cracker thing. And it tells you what the amount of energy is per serving, right? So how much is a serving? Well, serving size is 14 of these crackers, whatever they are. So you get from those 14 crackers 130 calories. Now the thing about the nutritional calorie is it is slightly different than the regular calorie we talked about before. All right, this nutritional calorie here has a big C associated with it, right? And uppercase versus lowercase, I mentioned, makes a big difference. And this means 1,000 of the regular calories. So a nutritional or a nutritional calorie is actually a kilocal, 1,000 of the regular calories. All right, and that's where our relationship here comes from. So whenever you see calories being represented or being talked about from a nutrition perspective, by default we are referring to the nutritional calorie, right, which is the big C calorie, and that's 1,000 of the regular calories. Right, so that's a kilocal. And that would be 4,184 joules or 4.184 kilojoules. So that's one thing to keep in mind, because oftentimes you just see calorie and you think it's a regular one. Well, what perspective or in what environment are we looking at? Is it in terms of nutrition or is it in terms of other things? So how do we know? How does whatever this company is, let's say it's like Nabisco or something, how do they know that 14 of these crackers provide 130 calories of energy? They take 14 crackers out and it kind of feels like 100, well, maybe it's 150. Maybe we need to change it. How do they know that it contains 130 calories of energy? Do they just make it up? Well, I hope not. They actually can measure the caloric content of different foods using a device known as a calorimeter. Right? And the way that this calorimeter actually works is really, really simple. What you do is, what you have is a sort of a self-contained or a sealed container. You have a bunch of water in here, and in the middle of it, you have a compartment. And in this compartment is where you're going to place your food sample. So in this case, we can place our serving size, whatever, 13 of those pieces of the cracker. We stick them in here, and all we're doing is we're just burning it. And as it burns, it's going to give off energy. It's going to give off heat energy. And as it gives off that heat energy, where is that heat energy going to go? The water is going to absorb that heat energy, and the temperature of the water is going to change. So if we can measure the change in the temperature of the water, we can do a couple calculations and figure out how much energy was actually released from this thing when we burned it. Because what do you think happens when you eat that food sample as it goes into your body? You're burning it, right? It's not a big fire, though, that's burning inside of you. Right? That would probably be counterproductive. But there's a bunch of really, really, really tiny fires that burn progressively. And eventually they give you the same amount of energy. Right? So it's a very simple idea. And obviously, very sophisticated instruments are used. But the idea behind it is really simple. Right? You burn something, you measure the heat that's given off, and you can use that to calculate how much energy is in that food sample. So as you probably know, different types of foods have different amounts of energy associated with them. So for instance, sugars or carbohydrates produce about 4 kilocalories of energy per gram of sugar that you burn. Right? That sugar could be something like glucose or table sugar, sucrose, for example, or starch. That's the typical energy content of your sugars. Proteins have roughly the same energy content as your sugars. Right? About 4 kilocalories per gram of carbohydrate or 4 kilocalories per gram of protein that you burn. Fats, though, are a little bit more energy stuffed. Right? You get just over 2 times as much energy per gram of fat than you would for the same gram of protein or the same gram of carbohydrate. Right, you get about 9 kilocalories of energy per gram of the fats that you burn. So carbohydrates and proteins have the same energy content. And then your fats or your lipids are going to have twice as much, about twice as much. As the others. And the reason for that has to do with how the the fats are actually broken down. And it's really, when we get to the metabolism down the road, we'll actually see how the digestion or the breakdown of fats varies tremendously from the other two. That leads to the difference in energy content for the different types of foods. So needless to say, your foods that have different amounts of carbohydrates, fats, or proteins are going to have different amount of energies associated with them. Right? So for instance, something that has a lot of fat in it, like a steak for instance, lots of fat, 27 grams of fat, is going to have a lot of energy associated with it than something that only has sugars in it, like an apple, which only has carbohydrates, no fat, no protein. And the energy content here is a lot less. So knowing what the energy or what the components of a food sample is, we can actually calculate how much energy that food should generate. All right, so let's take a look at an example. We're told here a cup of whole milk. That's the good stuff. Right? Whole milk contains 12 grams of carbohydrates, 9 grams of fat, and 9 grams of protein. How many kilocalories does a cup of whole milk contain? All right, so as you pose with any problem, you want to organize the information. All right, so we're given how much of each of the different types of foods or the different types of molecules we have in this cup of milk. So we have 12 grams of carbs. I'm going to abbreviate carbohydrates as carbs. You have 9 grams of fat, and then we have 9 grams of protein. Right, and we need the total energy content of that 1 cup of whole milk. So in order to get the total energy for that cup of whole milk, we would need to first of all calculate how much does each of these components of the whole milk provide. Right, so if I have 12 grams of carbohydrates, how much energy would that provide? If I have my 9 grams of fat, how much energy would that provide? And if I have 9 grams of protein, how much energy would that provide? So we're going to use the energy content for each of those 3 types of food, right? And that's our energy content here. We're asked for kilocalories. So we're going to take those and we're going to use them as conversion factors in our calculation. So for instance, if I have my carbohydrates as 4 kilocalories per gram, what that is telling me is I get 4 kilocalories of energy per gram of carbohydrate. Right? That is what that relationship is telling me in terms of something that I can use as a conversion factor in a calculation. Similarly, the fat here is telling me that I get 9 kilocalories of energy for every gram of fat. And then for the protein, right, this is telling me that I have 4 kilocalories of energy for every gram of the protein. Right, so those the energy content per gram of each of these things I can use, I can incorporate as conversion factors in my problem. So let's go ahead and insert them in. I left some space next to them so that we can put them in using our dimensional analysis method. So 12 grams of carbs, and I'm going to use my conversion factor, and that says that for every 1 gram of carbohydrate, I get, how much was it? 4 kilocalories of energy. So my grams of carbs can cancel. That's going to give me the amount of energy for that amount of carbohydrates. Similarly now, for the 1 gram of fat, or for the 9 grams of fat, sorry, I can use my conversion factor, which tells me for every 1 gram of fat, I get 9 kilocalories of energy. Grams of fat cancel. And then for my protein, I do the same thing. I use the conversion factor for the protein. For every 1 gram, I have 4 kilocalories of energy. So I calculate the energy amount for each of the components, whatever these end up being. And then to get the total amount, what am I going to do? Just add them all together. All right, so I'm not going to go through the calculation with you. All right, I'm going to have you do that on your own. So I'm just going to say this is X, this is Y, and that's Z. All right, so the total amount then, the total energy would be X plus Y plus Z. And again, don't forget your unit here will be kilocalories. Okay, does that make sense? So knowing, you have to know, or you can look up what these values are, right? What the energy content per gram of each of these things. Then we can stick them in as conversion factors to calculate the amount of energy provided by that amount of the component of the food or the drink or whatever it is that we're dealing with. Okay, so one thing that we also need to be aware of when it comes to looking at energy and energy content of different foods is how that affects the ability of someone to either gain weight or to lose weight, right? So when you go through your regular day, you are using energy, you are expending energy as you walk from your car to the classroom, or as you go to the gym and you work out, you're expending energy. Even if as you're sitting there taking notes, your heart is beating, and that's expending energy. In order to expend energy, you need to eat stuff so that you have these fuels to burn, to provide that energy. So if you have an energy imbalance, that can lead to one either losing or gaining weight, for instance. So if your energy input is more than energy output, so you're taking in more energy, more calories than you are expending, then that will result in a gain of weight. Right? So you're taking in more than you're actually losing, and then the alternative or the opposite would be true. So if you expend, so if energy input is less than energy output, and that's how you lose weight, right? So you're burning a bunch of calories and you're not replacing all of it. So you have a net loss of calories, a net loss of energy. So that's generally how there's, the difference in whether somebody loses weight or gains weight. And that has, this is just a summary statement of these two things. What can lead to a person energy input being less than energy output? Well, it can be your diet, but it can also be due to what you actually do on a regular basis, right? Your activity level. So there are several factors that come into play, but overall we can say that weight gain or weight loss is just a balance between how much energy you're taking in versus how much energy you're actually expending. All right, and on the right side here you have some typical guidelines and energy requirements. I think these are from the FDA, or the Food and Drug Administration, for how much energy you would typically need if you were a male or a female in a particular age bracket or age group. Again, these are average values, right? Depending on your metabolism and how easily you burn calories, this may vary slightly, or maybe more. All right.